So let us start. Good evening, everyone. So this is the last session uh, for this course. So we will discuss some examples related to the base isolation, and we have I have planned an extra live session on Thursday. The timing and the schedule will be inform you soon from the PMRF team. So that we will discuss later. So if you have any doubt or something else, we you can discuss me here. Like one of the doubt was from the Mahesh. You didn't read the peak response that is asked, and then you calculate directly summation of the total response.
Yes, sir.
So that peak model response was mentioned there. So you have to be careful when you read the question.
Yes, sir. Yes, sir. But just for a concern for this time, can you favor for that?
No,
Like
because it is no because
every question they have not mentioned. Like I have a doubt in the when I am doing that, I have a doubt, but what
you
I
you
can
you,
do.
you should ask these things before the deadline so that those things can be cleared. But
But
after the solution release, now that range cannot be updated because some other students also has done that using the peak response, so it is unfair with them. So
like very small range has there. That's why I have asked.
the range, about the range, I don't have the idea what was the range, but the procedure was that same.
Thank you. Okay. Thank you.
So is my screen is visible?
Yes,
Yes,
sir.
serviceable.
Okay, okay, so please mute yourself. So in this session, we will be having like some objective type of question and then the analysis of the base isolated building. We will have that kind of questions. So we will discuss them one by one. So the first question. So the first question is that uh, the following is the base requirement of the seismic isolators. So what are the basic requirement for the base isolation? It require high vertical stiffness with low stiffness, or it require high horizontal stiffness with low vertical stiffness, or the high relative deformation in the superstructure with low deformation concentrated at the isolator level, lengthening of the time period, reduction in the displacement with the high energy distribution. So can you tell me like what was the answer for that? Like which are the main requirement for the seismic isolation? Anyone?
I think A is correct. High vertical stiffness with low horizontal stiffness means horizontally it needs to be flexible.
Yes, that is correct. We need the seismic isolation should be flexible in the horizontal direction, and stiff in vertical direction. Any other? High horizontal stiffness with the low vertical stiffness? It is not, because if we have the higher stiffness in the horizontal direction, then that become more stiffer. So it won't be fulfill the purpose of the base isolation. Another is the high relative deformation in the superstructure with low deformation in the isolator level. So is it okay or not?
No, sir. Isolator level deformation more and superstructure would be less, I think.
Yes. So when we design the isolator, we it is requirement, or it is like it should be there, like there is not much deformation in the superstructure, within the superstructure. The whatever deformation come, it it can it taken by the isolator level. So that option is also wrong. The another is the lengthening of the time period, which means reduction in the displacement with the energy dissipation. So can you tell me, is it okay or not? So our seismic isolation principle, main basic principle of the seismic isolation is what? It works on the lengthening of the time period. Okay. So like let us suppose my structure time period is at here, TB fixed base, uh, TF fixed base. So if I increase the structure time period from TF to TB, so in that case what will happen? My acceleration is reduces. So my forces will be reduces. If my forces is reduces, one thing, but at the same time, if I increase the time period, will my displacement is increase or decrease?
It will increase, sir.
It will increase. So this is a, when the time period is increasing, my acceleration is decreasing, but with the increase in the time period, my displacement is actually increasing, like that. So let us suppose if it is a TF, and if we take it the TB, so my displacement is higher. So how can I control my displacement?
We can increase the damping in the
Yes.
system.
So if we include the damping in the system, I can control my displacement. Okay. So that D option is also correct. Like time period, lengthening of time period with high damping. Okay. So these two options are correct, and these B and C are wrong. So now the another question. An increase in the damping ratio lead to the following: increase the displacement of the response. This is the very simple. Can you tell me by reading it out? Like if I increase the displace, like same is the, like the fourth option we discussed. If I increase the damping, what?
Reduce the displacement. C option, sir.
Yeah.
Yes. So that is the C option. Like with increase in the damping, when the damping is increasing, my displacement or the spectral displacement, spectral expression, all will be decreases. Okay. So increase in displacement response, it is wrong because damping is not increase the displacement. It is also wrong, and the damping has no impact on the response. It is not possible. Okay. So that was the one question. Now we have a like some, when you solve the question, you have some idea like how do we define the stiffness of the isolator system or something else. So we have given a time period of the structure, which has the t is equal to zero point 0.6 second. Okay. Mass of the structure is given as 100 tons. Okay. So it is proposed to be seismically isolated using the base isolator. Which of the following stiffness of the isolator system would be the most effective in the isolation system? So do you know how to solve this? That same kind of problem you have in the assignment as well. But at that, in that assignment, I think the period or the mass is asked. Like some reverse procedure is there. So you have the time period of the structure, you have the mass. So how do we get the which stiffness should be there, so that the which stiffness is best suited to our isolation system, so that we can use it? Anyone?
I exactly don't know, but time period is given, means frequency is given. So we can take that ratio of frequency, and that should be around 10 raised to minus 2. So from that, if we go to stiffness, like that, can we do?
That is might be another way, but here what we do, First calculate the time period of the structure. Time period of the structure is there. First calculate the stiffness of the structure. So the stiffness of the structure would be omega n square by k by m. So k would be m time omega n square. So omega n would be 2 pi by Tn. So Tn is your zero point 0.6. So calculate the time period, how much omega n, okay, and using that you can find out what would be your. So the my frequency omega n is coming out to be 10.47 radian per second. Okay. So my stiffness become m is the 100 tons. So that is the 100 into 10 raised to power cube to convert into kilogram and then multiply with the 10.47 square. So it will be coming out to be some 1096622 Newton per meter, or we can write it into the kilonewton. So that would be the, or we can call it as a 11,000 kilonewton per meter. So this is the stiffness of the our superstructure. So the isolation system should have that much flexible, so that we should have the, if we compare the which stiffness would be best suited, like the flexible system, like whichever the, if we compare with the four options a b c d, so we want like a gap between our the superstructure time period like zero point 0.6, and we want our time period of the base isolator is higher. Okay, so which one give the higher time period? A, 1000 kilonewton per meter. Okay, so if we compare with the all the available four options, compare with the four options, K is equal to 1000 kilonewton per meter will provide better isolation system. Okay. In your assignment, I think there was a question in that the you need to find out the mass. So in that your mass would be higher, so that it will lead to the higher time period. Is it okay? Are you getting me? Any doubt? Anyone?
Sir, how we taken the lower k means
Like we have the, like I can calculate the, like I have the stiffnesses are available. So I want what I want, like my time, there should be a significant difference between the superstructure time period and the base isolated structure time period. Is it okay? So it would be,
yes sir.
it would become when my structure, when my stiffness of the isolator would be lesser.
Keeping the mass constant
Mass is the like the 100 ton is there.
means both of superstructure and base isolation.
Yes, like here, like actually in the base isolated structure we have the base mat, something like that. Okay, so we have
Yes
the
sir.
mass m, so you can take some percentage of that mass it here base mass, some 2 by 3 or 1 by 3. Using that you can calculate the
Okay.
time period. So which one would be give
Okay.
you the time higher time period? Obviously when you consider the option A.
100K. Yes sir. Yes sir. Got it sir.
So like if your stiff, whenever your stiffness is lesser, mean your time period would be higher.
Yes 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 yes.
So that's why we need to use this. Or other, in other case, if your mass is higher, then our time period is higher. So here we have the mass is the given constant. In some cases stiffness is given to you, then you have to compare with the mass. So that's how you can do the things. Or in some cases time period, like You have given the base isolated time period, then you have to find out like which one would be the better. So there is a gap between the base isolated, like more the gap between the base isolated structure and the fixed base structure, your isolation would be the best effective. That's the thing. So there should be significant gap between the fixed base time period and the base isolated time period. Is it okay?
Yes, sir.
Okay. Then we solve a problem, like we will analyze a base isolated one story building, and then we compare, okay, how the my like the base shear and the displacement in the building will affected. Okay, so we will do that. So you have given a fixed base building. This one is the fixed base building, okay, and this one is the base isolated building. Okay, so we have some given data in that question. Okay, we are not going to design the base isolated here. So we have given the data for the fixed base building. For the fixed base building, we have the time period TF of the fixed base is the zero point 0.4 second. Damping of the fixed base building is the 2%. Okay, and we have the data for the base isolated building TB. We have the time period of the base isolation is the 2 second, and damping of the base isolated is the 10%. Okay, so this is the mass. Mass is that, and the we have given the base slab mass MB is taken as a 2 by 3 of M. Okay, so when we add a, like it is a single degree of freedom system, when we add a base isolation to the system, there will be one more degree of freedom. Okay, so this become, so this is the single degree of freedom SDOF, but this become as a MDOF. Okay, 2 degree of freedom system. Okay, because the base isolated is there. So for this, first we need to calculate what is the, what are the modes, what are the modal time period that we need to calculate. So for this, the stiffness is K, and that is okay. So the stiffness of this is KB. Okay, so the stiffness of the base isolated building, the properties I can write it here, how the those things can be calculated. So we will analyze only the base isolated building, and we can compare with this the superstructure directly single degree of freedom system. Okay, so for the base isolated building, the base isolated period can be calculated by 2 pi divided by the omega b. This is the seismic base isolation period, not the model. Like the I have the isolator, and isolation time period is the, like if I have the isolator, the time period of this isolator is the TB is the 2 second. Okay, and that I have applied it here. So TB is given this like, and that omega b is calculated as a KB, stiffness of this, divided by M plus MB. Okay, and damping of the xi b is calculated as a CB divided by 2 into M plus MB divided by omega b. Okay, so for this, first we need to develop the mass matrix, stiffness matrix of the system. Okay, so the base isolated, I can do it like that. This one, this one, this one. So this is M, this is MB, this is KF superstructure. Okay, and this is KB. Okay, so using that, I can develop, we can develop a mass matrix and the stiffness matrix. where the MB is given as a 2 by 3 M, and the KF we will calculate. How do we calculate the KF? KB. So the KB can be calculated as a, so TB is given to me as a 2 second. So the omega B would be what? 2 pi by 2. That would be the pi. Okay. So the KB would be omega B square into M plus MB. Omega B square is what? Pi square M plus 2 by 3 M. So if I add it, how much it would be? Anyone can get me this? So
16.449.
16.45 M. Okay. So this is the KB. Okay. Similarly, we can calculate the KF. Can you calculate the KF? So for the KF, that would be the omega F square time the mass, and omega F is what? 2 pi by, how much is the TF? Is given to me zero point 0.4 second. Okay. So how much it is? 2 pi divided by zero point 0.4. So that is 15.70 radian per second. Okay. So my KF would be 15.70 square times the mass. So that would be coming out to be 246.74 M is my KF. So now can you develop the mass matrix and the stiffness matrix? Damping matrix we will develop later, but before that, to find out the model properties, we need the mass matrix and the stiffness matrix. So develop those. This is the 2 degree of freedom system normally, so I don't think it would take time. So at the base isolated, I can call it as a degree of freedom 1. It is 2.
263.19
Okay.
M.
Okay. What is? You are
263 point.
giving the stiffness matrix, no? Okay.
Yes.
So stiffness matrix would be K is equal to KB plus
KB
KF
plus KF
minus KF,
minus KF minus
KF,
KF and KF.
KF. So when we calculated it, it will be coming out to be 263.19 M
19 minus 246.74.
0.74 M minus 246.74 M and 246.74 M. So this is my stiffness matrix. And can you give me the mass matrix? That would be simple. 2 by 3 M 0 0 M. Okay. So can you find out the time period? Like we need to solve this K minus lambda M is equal to 0. So that would be the 263.19 M minus 2 by 3 lambda M, 246.74 M, 246.74 M, and 246.74 M minus lambda M. Okay, if you do that, 263.9 m minus 2 by 3 m lambda into 246.74 m minus lambda m minus 246.74 square m square is equal to 0. So m will be go there. So if I will take the m outside, that would be the m square. So that would be 263.19 minus 2 by 3 lambda into 246.74 minus lambda 246.74 square is equal to 0. So m square cannot be 0. Okay. So this will be 0. And solve this and give me the lambda 1 and lambda 2. Please solve this. Anyone with the lambda 1, lambda 2? So if you solve this, I am getting lambda 1 as a 9.6351 and lambda 2 is the 631.89 or something. Is it okay? Are you getting the same? Anyone? So using that, can you give me the omega 1, omega 2 and T1 and T2? Omega 1, omega 2, T1, T2. So the omega 1 would be 9.6351. So that would be I am getting 3.104 and omega 2 I am getting 631.89,
Omega 2 is 25.13.
25.13 radian per second. So T1 would be your 2.0242 and T2 is your 0.25 second. Okay. So corresponding to this, you can find your mode shapes. So we can observe like our base isolated time period was what? TP was what? 2 second. So we can
Yeah, yeah. We can say that SDOF uh, time period we can take.
so that over time period of the first mode is the 2.024. It is increased little bit. Why it is increased? Anyone? Why it is increased? It increases because of the there is some flexibility in the superstructure. So that's why
Yes, yes.
it is increases. So now calculate the mode shapes. So if you calculate the mode shape for lambda 1 is equal to 9.6351, your phi 1 is coming out to be minus 0.756 minus 0.7867. Can you normalize it with respect to the degree of freedom 1? And the lambda 2 was that 631.89. So your mode shape phi 2 was minus 0.9638, and that is 0.6173. So if I normalize it corresponding to degree of freedom 1, how much did I get? That would be the 1, and that would become 1.041. Do you know how do I get the normalize?
Yes.
Like I divide it by the, like I want to normalize with this 1, so I will divide it by the minus 0.756. Okay, same for this one, I divide it by minus 0.9638. Okay, so if I do that, I'm getting this is a 1, and this one is I'm getting minus 0.641. Okay, so if I plot MB M, if I plot in the first mode, I have it 1, it here, so that will be deformed like this one, and then it will deform like this. So that is 1.041, that is 1. Okay, so that is 1.0, 1.041, with T1 is equal to 2.024. Then the mode shape 2, in that it is 1, and then in the negative it would be 0.641, but T2 is the 0.25 second. So now after getting this, I need to do model response analysis. So the model analysis, how can we do that? We can find out the SN, like if we need to find out the uh, base year, what we were doing, we were finding out the SN model expansion, gamma n times mass matrix times phi n. Okay, so our structure, like let us suppose it will be having some m 2m by 3, it then it will be distributed in some masses, Sn, S1, S2. So to find this S1, S2, we need first participation factor. So can you give me the participation factor? Phi 1 transpose mass matrix times the phi 1 divided by the phi 1 transpose mass matrix phi 1, not this one, this would be the L. So the L is what? If the ground motion is applying in this direction, so my influence vector L would be what? 1, 1. Okay. So using that, can you give me the gamma 1 and gamma 2? Please try. Similarly, gamma 2, phi 2t, mass time L, phi 2t, mass matrix, phi 2. So find out that gamma 1 and gamma 2, so that we can find out the S1 and S2. Can anyone give me the gamma 1, gamma 2?
Gamma 1 is 0.975.
Okay, so that phi 1t was 1.041 1 time 2 by 3 m 0 m 1 1. So it was coming out to be 0.9756. Okay, now gamma 2, it would be as minus 0.641 1 2 by 3 m 0 0 m 1 1. Anyone with the answer? How much we are getting gamma 2?
0.023.
0.0238. Okay, something like that. So those are gamma 1, gamma 2. Now we will calculate the S1, gamma 1, phi 1. So gamma 1 is the 0.9756, mass matrix 2 by 3 m 0 0 m times 1.0411. So give me that S1. Similarly, S2 can be calculated as a gamma 2. So what you are getting S1 and S2?
0.65.
0.65.
Yes.
So that would be the 0.6504. Okay, that was 0.65, 1.015, and in that it was 0.159. So we can write it as a 0.16, and that is 0.153. Okay, so are you getting the same?
There are eigenvectors. Uh, you have to change that. But eigenvectors.
Eigenvector is the same. Okay, you are saying it is like I have put it in the reverse.
Yes. Yes.
Yes, but okay, but those values are correct. Okay, that would be 1.041, 1.041, 1.041. It is one. Is it okay now?
Yes, sir.
So now after getting that, now we have this one. So at this place we have 2 by 3 m, and at this place it is m. So that would be the 1.015 m, and at this it would be 0.651 m, plus at this it is a 0.16, at this it is 0.153 m. So how much would be the base shear? Can you tell me in the first mode? So the base shear would be VBN. In the first VB1 is how much? 1.015 m, and in this case VB2 would be minus 0.15 m. Okay, so for finding out the these are the S1, S2, and in term of the m, to convert it into the forces we need the acceleration. Okay, A1 T and A2T. Okay, so corresponding to TB is equal to 2.04 and 0.25, we have the response spectra. So in this, corresponding to 2.04, I have acceleration which what? 0.359. But for this, we need to check whether we have to look at the because the damping is the model as the 10%. but those damping are for the isolator. We need to find out the damping in which each mode also. Okay, so before going that, we can find out the damping here. Can you give me the model damping? Like let us suppose I have a two-story building. Okay, which that is a xi fix, xi b. So can I find xi 1 and xi 2 in each mode? If I have the xi b, because the damping of the base isolator is at xi b, which is a 10%, xi f is the 2%. So how do I calculate the xi 1 and xi 2? If the each story is given to you as a different damping, so how do we calculate the model damping? Anyone? Anyone has any idea?
Alpha into mass matrix.
So how do we can do the relay damping we use when we have the model damping of particular two mode we know, like some mode we know, and then we need to find out the for the another modes. Then we can use the relay damping. So for this, so we are not doing the classical damping. So if I have the JIB 10%, can I calculate the CB? And if I have the JIF as a 2%, I have to calculate the CF. So JIB would be what? 2 JIB M omega B, and CF would be what? 2 JIF M omega F. So that would be 2 JIB how much? Zero point 0.1. M is how much? M plus 2M by 3. Okay, and omega v was what? 2 pi by 2. Not the model time period, only the time period of the isolator. And for the CB, 2 into 0.02 time mass time 2 pi by zero point 0.4. So can you give me the CB and CF now? Can you give me the CF and CB?
The CB is 1.047.
So CB is 1.0471 m and CF is
0.2.
0.628. Okay, CF and CB. So what is my damping matrix C? It would be have like the mass matrix or the stiffness matrix. How it would be?
It would like a stiffness matrix.
So it would be like a stiffness matrix. So calculate the matrix, write down the C. So CF plus CB is how much? 1.6751 m, 0.6284 m, 0.6284 m, 0.6284 m. So now I have the C. So to find out the damping, model damping, what is that? 2 xi n mn omega n. So for the first mode, my xi1 would be C1 by 2 into m1 time omega 1. So C1 would be what? Phi 1 transpose C time phi 1. M1 would be phi 1 transpose M time phi, and omega 1 is what? 2 pi by 2.024. So that is 3.1043 radian per second. Can you give me the C1, C2, C1, M1? And for the second mode, Xi2 would be C2, 2M2, omega 2. So C2 would be phi 2T, C time phi 2, M2 would be phi 2, M phi 2, omega 2 would be 2 pi by how much? 0.25. So calculate. So now calculate C1, M1, C2, M2, and using that calculate the damping and give me the answer. Anyone with the Xi1, Xi2? So my C1 is coming out to be, when you put the values, see the C matrix, it coming out to be 1.0477, and C2 M1 is coming out to be 1.75, 0.03. M will be multiplied, so that will be cancelled out later. Similarly, C2 is coming out 2.7389 M, and M2 is coming out to be 1.075 M. Now using those things, can you give me the damping ratio? You have the all three values now. So give me the damping 1 and damping 2 in each mode. Anyone? If not, let us find out the damping. So the damping is C1 is 1.0477 M by 2 into 1.7503 M times 3.1043. So it gives me 9.65% damping. Okay, and if I will calculate damping 2, damping in the second mode, it would be 2.7389 M by 2 into M2 is how much? 1.0775 M times 25.132. So if I calculate it, I am getting 5.06%. So you can observe like my damping in the first mode is nearly 10%, like near to that. So due to some little effect from the structure, it reduces to 9.65. Okay, and in contrast, due to high damping from the isolation, my second mode damping is changed for the like that is the second mode is what? It is the superstructure mode. So that changed from 2% to the 5%. Okay. So these are the non-classical damped system. So now using that, now you have the time period 2.024, damping 9.65%. Corresponding to I want to find out A1T. For T2 is equal to 0.25 second. Xi2 is 5.06%. I want to find A2T. Okay. So when I go to the spectra, so in the spectra I can see like I have the curve for the 10%. If I need to do exact, then I need to find out the curve for the 9.65%. So here we are going with the 10%. So my A and A1T would be the 0.359 G, and corresponding to T2 near in the 5% damping curve. Okay, A2T is 1.347 G. Okay, so if I write it here, so these are 0.359 G, and that is 1.347 G. Okay, so now we can make a table to compare the base shear and the deformation. Okay, is there any doubt up to this point? Anyone? Anyone? Am I audible? Okay, if not, then okay. So I let us make a table. So for the base shear, base shear in the mode 1 2. What is the an? In the mode 1 it is 0.359g. In mode 2 it is 1.347g. What is my vb? And for the first mode I am looking at the base, only at the base. So that is 1.015 amp, and that is minus 0.15, minus 0.15, not the 0.15. Okay, so that was, so that would be 0.016. Okay, so that will come out to be 1.015 amp in the mode 1 and minus 0.015 amp vbm. So you can multiply it with the acceleration. So if you multiply with this 0.359g, so that v at this, and let us take a ratio of m because we are considering m as a constant. So how much that would be? 1.015 time 0.359 time 9.81. So how much it is coming out to be? So we are taking the ratio of not the m, we are taking w, weight, v by w. So in this what we do, we simply multiply with the 0.359 because the we have the m and g, mg would be the w. Okay, weight. So it is coming out to be 0.364, and in this it is coming out to be 0.021. Okay, so when I take the base year using the srss, if I do the srss, so I am getting out to be my base year 0.365 ratio. So this is for the base isolated building. Okay, if I taken this fixed base building in which that is actually SDF system, in which TF is a point 0.4. So corresponding to TF is equal to zero point 0.4. If I look into the time period corresponding to the zero point 0.4 for the 2% damping, it is nearly how much? 1.830g. Okay, so for the fixed base, my acceleration A and T is how much? 1.083. 1.830z. Okay, so here what is my, that is the mass. So my base here vb would be how much? That would be the m. Okay, and if I will take the ratio vb by w, so that would be the 1.83 is the ratio from the single degree of freedom system. So if I compare the this, if I compare the base year for the base isolated building at like vb by w ratio, and the for the fixed base building, I can get how much difference it is coming, how much reduction it is there. So can you get it? How much difference in the base isolated building in the fixed base in the shear? If you get the percentage in the fixed base building, that is around 180%, or the about 5 time you can say we have the we have the base shear in the fixed base. So using that isolator, how much base shear is reduction in the building?
Uh, I have a doubt.
Yes,
We are finding the base shear at base isolation, top of the base isolation, right?
yes.
Okay. If you want to calculate bottom of the base isolation,
That won't over useful, because that is the mat, because our column will start above that mat. So we are interested in finding out the shear in our columns,
can you please explain once? I didn't
like
understand.
how our base isolators are applied to our buildings. Like this is my building, single degree of freedom system. This is a fixed base. Okay, so I am interested in the base shear at the column. So this is like the fixed base. Okay. Now the second one is that at the base, like ground, I have providing it the mat base foundation base to for the isolator, and then I am putting the isolators it here. Okay. So that what I have to design the columns. So how much base shear is coming into my columns with the using the base isolator, I need to interested in these columns. Still you have doubt?
Actually, I am not getting because uh, uh, in foundation we have to come up the columns coming from the foundation, right?
Yes,
Uh, when the ground level, when you start a superstructure,
yes,
the foundation will come from the columns come from foundation.
yes.
Then where we place this base isolators in
Between
between
the
columns, right?
when your foundation is over,
Okay.
or about that our base isolation start, like what happened, actually you can do many ways. Like over, like these are the, like let us suppose foundations are coming from the bottom. Okay, then what we do, we put the isolator on the foundation. Okay, or you can take a some pedestal above that. Okay, isolator put on that, and then we make a mat slab, so
Okay.
that it should distributed uniformly. And then above that,
That mat foundation also like the concrete, right?
yeah, it would be concrete.
Okay. Then
Then
uh,
above that mat foundation, my column would be start. That is the one way. In another way, some of the
how
cases,
column is connecting with okay, you have placed a mat, right?
so from the column would be from the mat foundation
From mat only. Okay. There is no connection between the column and
and
the
found,
foundation.
yes, that is isolating them.
Okay, okay. But when in the class, Sir has shown one video that is like in a ground floor. After
Yes,
uh,
that video was what, like that. I am thinking you are talking about that. There are some pedestal kind of things are coming from the parking lot, if you see, and
yes, yes,
at that you have the isolator. Okay, and then your beams and the columns are resting on that. That was the that is the image from the Bhuj earthquake, I think. Bhuj hospital in the hospital in the Gujarat, in the Bhuj, after the Bhuj earthquake, they have isolated that. So what they do, they have taken the pedestal about the 1 or 2 meter height, or on that they have put it the isolators. On
okay,
that they have started the construction.
okay, okay. Then the columns are started from above the base isolators.
Yes, in the like the yes, the column and that everything superstructure is about that. The base isolated. In the that picture that sir shown, in that actually those are the pedestal. Like from the footing, we have taken the above some 1 meter or 2 meter height, so that our isolator can be placed. On that we have the, like we have the our beam structure, beam and water column, and then the column is start also from that.
That means a base isolator should resist the whole weight of the.
Yes, that would be resist the whole weight of the superstructure.
Oh, okay, okay. Then cost also like will increase, right?
Cost is like that depends. In India, like nearly if you go with the one isolator with the proper manufacturing and the design, you will get for the one isolator around 30 to 40,000 for the one isolator. And that depend also how much flexibility, how much, if you require the more soft rubber, the natural rubber, then the cost will be increases as you go with the like the soft rubber. So
Sir, what type of connection is there between that isolator and concrete means?
actually
Yes,
How
sir.
are
what
they fixing?
actually what happen, your isolator is there like that, okay. In that there is a bearing plate in the isolator, okay, steel plates, okay. So these steel plates are mounted in the foundation like that. Like in the concrete also they can mount the plate, or they can some nut bolting or something else, through that they are mounting it.
Can I find these type of structures in our next class? Like,
Okay, you want the real examples of those things, okay.
yes, yes, yes. I'm
I have
expecting.
Yes, sir. Yes.
I will show the images. I have the video, one video. If you want to see the video, I'll share a link. Let me share you the link, which we have the made that model kind of things.
Okay, thanks.
So in the India reality, we have the one the hospital in the Simla, and one hospital in the Simla. One is the police station in the Bihar.
Sir, how often we use this base isolation means I don't know the how much frequency is used means is in multi-story structure it is used always or it depends
It
or what
de-
is the scenario in India?
in the multi-story that can be used, but for that we have to design according to that, because in the multi-story we our time period is already high. So in the
Okay,
India we like we are not going for the multi stories, though are like around 2 3 degree of 2 3 stories, like, or the one story. Like in India they are normally doing for the important structures such as a hospital, and that so that after the earthquake they should be functionally working. Like we do not want, like, at least those structures should work, so that that can help us during that. That should be in the operational basis.
okay, sir. Means for important structure we are using this base
Yes, in
isolation.
India, because if you go with the that always that increases the cost, but now the research is going on with that, the developing of the base isolator with the scrap tires. So those tires, like after those, like the scrap. So with that scrap tire, our isolator, if like in our lab, it is also going on. If that is successfully done, then the isolator's cost will be reduced significantly, around 5 to 10,000 it would be available. So those kind of
Okay, sir.
research are going on when it's the, because if you use the for the normal building, the cost will be the very high, it increase significantly.
Sir, we are placing the base isolator so that we increase the time period, right?
Yes.
But if you increase the damping, the displacement will reduce, right? Then how can we place this type dampings?
Actually, the when we design an isolator itself has a high damping. Actually, whenever you see in the isolator has like inside included a like the lead rubber core, lead core. So that has itself high damping. Rubber itself has a high damping. So it has the damping around 10%, 20%, even 30% has the damping in the isolator. So that is incorporated within the isolator itself. You do not need to provide the some additional devices for the damping. You do not need to do that.
okay, okay, sir.
So those kind of things are already available in the isolators. So I will show you some examples of the I have shared the two link of the two videos. So that is developed by us, like our lab mates. So you can look into that in the some of the buildings as isolator is there. You can play it now if you have the option, and you can look into that. Are you able to access the videos?
Yes, yes.
So you can like it is a short video. Those are short videos. So that one is developed during the Tech Connect. That is the one first in our IT Bombay. So during that we presented that model, and the one is like that video to explain that how that earthquake can affect the buildings, and then how do we come up with the solution with the isolation. So you can take 2 3 minutes to watch that video so that you can get the clarity how those things are, uh, how those things work. So you can watch the video. Are you watching the videos?
Yeah, just I have.
Yes, yes, please watch so that it will be easy, very good to see you like how the things were look like.
Yes, yes. Okay.
Yes, sir. We have watched videos.
So did you get some like some certainty like how those things work? Am I audible? Am I audible?
Assistant professor.
Okay.
Am I audible?
I, yes, sir. Yes, sir.
Actually, my network has lost due to some issues. I think my screen is not visible.
Yes, it's not visible.
So let me connect. My internet is not working, so that. Is it visible now?
Yes, sir. Visible.
Okay. So you got those, like you got the review about the how the isolator is work. So now you can calculate the isolator deformation. Am I audible?
Yes, sir.
Okay. So you can calculate the isolator deformation. How do we get isolator deformation? That we are getting it is as a some 34 centimeter. So can you calculate this? This is not like that. That would be the an a1 divided by omega n square, omega 1 square, a2 divided by omega 2 square. So can you calculate this? A1 is how much? 0.359 times 9.81 divided by 3.104 square. So that will be come into the meter. So I will do it into the centimeter. So it is coming out to be 36.55 centimeter. And for the second one, 1.347 into 9.81 divided by 25.132 square, and if I will convert into the centimeter, it will come out to be 2.091 centimeter. So to find out the displacement in this, I will need to multiply. Did you remember gamma 1 time d1 dn, gamma 2 time dn? Did you remember this?
Yes, yes.
So if you multiply this gamma 1, so we have calculated gamma 1 initially, if you remember. So that gamma 1 was the 0.976. So 0.976 multiply with the 36.55, you will get the isolated displacement as a 35.67 centimeter. And then gamma 2 is the 0.024 time 2.091, you will get it 0.051. So you can see like how much displacement you are getting in the isolation. So you have the displacement, isolation, deformation. The first mode, it is a 35.67. In the second mode, it is a 0.051. So if you want to find out the peak displacement SRSS, you will find out it as a, that will be 35.68 nearly centimeter. So this is your isolated deformation. So is there any doubt in this question? Like we can see how much base shear is reduced in the base isolated structure compared to the fixed base. I have a question. What if my, if like in this question we have the significant difference between the fixed base building which has the zero point 0.4 second time period and the base isolated at the 2 second. What happen if my structure and the base isolated has the same time period? Like let us suppose my structure also has the 2 second time period, and my building base isolated has also the 2 second time period. Then what will happen? It will work or not? Did you get the question?
Yes, yes. I
Yes,
think
sir.
it is workable when placing this isolation. We have more time period so that the response will be less compared to fixed base.
Like that, I don't have the space because I utilize that space significantly. Okay, so I have a question like that. In the first question, we have the fixed base has the time period of zero point 0.4 seconds, and isolated building has the isolator has the 2 second. Okay, if I have a case in which my fixed base building has time period of the 2 second, and if I apply the isolator, whatever the isolator is applying, that isolator time period is also as a 2 second, TB also 2 second. So will it be effective or not? If not, then why? If yes, then also why? So what happen if your structure is also flexible? Like that mean your structure is also flexible. And if you do the same analysis, whatever we have done, now we have considered the zero point 0.4 second, you have to consider 2 second. And if you do the analysis, you will get there is reduction in the, like the base here is not much. There would be reduction, but not much significantly. Like there is a reduction in 5 to 6% reduction. Will you get it?
Ah, okay, okay.
So there will be reduction, but it is not that. So in that, what is that? In this, the second mode is also not much negligible. So in this, what, like let me explain what are those points would be there. So in this, what will happen? The structure will not behave rigidly as behave in the previous mode. Rigidly in the first mode, like in the previously, in the previous question we have seen, like it was 1, and that the second mode, or like the in the degree of freedom 2, it was 1.041. But if you do that, in that case it will be, like if it is 1, then it would be nearly 3, or you can say 2.5, nearly this one. So in that case, the structure has also significant deformation. Okay, and the another is that the in the first mode damping inverse, that was the near to, like in the previous case what we get, the first mode damping 9.65. But when you do this, in this damping for the first mode will be coming out to be around 4.5%, so which has the more difference than the 10% damping of JIB. So this is because of what? Because that is also play a role, like superstructure is playing a much role in this. So that's why it has the larger gap between the dampings. So that was the for the for the flexible structure. One thing is that, like in the previous analysis, we consider our structure as some flexibility. You can do the analysis with considering the rigid, like your top superstructure as a rigid also. Then you will get the same answer, but that whatever answer we are getting with the considering this method, it will be coming out to be nearly same, not much difference. Whether you will get it by considering the fixed, there will be a little bit difference, but not much. Okay, so that was the for the base isolated. So we have the some simple question. Yes, anyone has any doubt?
Sir, base isolation is useful only when superstructure means is not much flexible. Means what
Yes.
if the superstructure is too much flexible? So then we can't use it.
Then we have to do another some techniques. We have to design our isolator such that it should have be utilized. If our structure is flexible, then why we need to do the isolator? First thing, if we need to do the isolator or something, if we need to do performance well, then we have to design our isolator such that there should be the sufficient gap. Then our isolator period not should be 2 second, it can be 3 second, it can be 3.5 second, like that.
Means we need to increase the damping in superstructure.
To get the effective
Means
base isolation, you should have significant difference between the isolated period and the fixed base period. That's all. To take the effectiveness, if your structure is flexible, like let us suppose in the previous question we have discussed, so we have find out that there is not much difference with the using the base isolator, around 5 to 6% reduction in the base here. So what does that meaning? If I will use that huge cost and I am getting 5 to 6% reduction, that doesn't mean for me at that time. Did you get it?
yes, yes,
So that we have a simple problem here. It is like a name of a like the isolator, but not that exactly the isolator. But I think it would be very useful to do a practice. Like in this question, a industrial saving machine has a mass of 430 kilogram and operate at a 1500 rpm. Okay, it appeared to have a rotating unbalance of magnitude and unbalanced mass, which is zero point 0.8 kilogram time m. Structure engineer suggests that the maximum repeated force transmitted to the floor is the 10,000 kilonewton. The only isolator we have, the one isolator availability, that isolator stiffness is given to us 7 into 10 raised to power 6, and the damping ratio is zero point 0.1. If the isolator is placed between the machine and the floor, will the transmitted force be reduced to the acceptable level? If not, what can we do? So, did you get the question first? If you get the question, what first we need to find out what is given to us.
This is like a previous question what we have done previously.
So, in this, we have given the, like, in the, if you remember from the transmissibility ratio from the unbalanced mass. Okay, what was our, in that case, what was our p naught was the m naught e time omega square. Okay, and your transmitted force limit ft max is provided by the engineer, that can be maximum 10,000 newton. Okay, so how much my p naught is, the m naught e is given to me zero point 0.8 kilogram per kilogram meter, and that the omega is given to me 1500 rpm. So can I convert it into the radian per second? 2 pi by 60. So that is coming out to be 157 radian per second. Okay, So if I will multiply this with the 157 radian per second, so I will get it as a 19719.2 Newton. So what is my transmissibility? What is my transmissibility? Force transfers maximum limit by the P naught. Okay, so Ft is how much? 10,000, and it is how much? 19719.2 Newton. So if you calculate this,
Point 0.5.
so that is coming out to be zero point 0.5 nearly. So using that, now this is the transmissibility. What is my natural frequency of the system of the isolator? So my natural frequency of the isolator, omega n, would be k by m, and stiffness of the isolator is how much? 7 into 10 raised to power 6, and that mass is 430 kilogram. Can you give me the omega n?
127.58 or
So
59.
127.6 radian per second. Okay. So if you remember the transmissibility curve or the response reduction factor curve, we are getting when our omega by omega n ratio is greater than 1 by greater than root 2, square root 2, my response is less than 1 for all kind of damping. Did you remember that?
Yes, sir.
So when our omega by omega n, so for this isolation, my omega by omega n should be greater than uh, under root 2, so that I can get the isolation. Okay. So what is the square root 2 value is 1.41, or but here what is my omega by omega n ratio? Can you get me the omega by omega n ratio? As omega is given to you 157 radian per second, omega n is how much? 127.6 radian per second. So omega by omega n, how much you are getting? Anyone?
1.23.
1.23,
1.23
23124.
less than root 2.
Okay, so it is less than root 2, means it will
Yes,
not
sir.
give me the effective isolation.
Yes, sir.
So what I need to do, I need to do something else so that I can get my isolation should be effective in that way. Okay, so that in that case, isolator will amplify the force. Okay, so my transmissibility limit is how much? 0.507. And what is my transmissibility? That is 1 plus 2r xi square divided by 1 minus r square 2r xi square. Okay, so we have the limit for the transmissibility is 0.507. Okay, so from this we have the damping as a zero point 0.1. Okay, like 10% damping. R you need to calculate for this, and you have the transmissibility 0.507. So using that, can you calculate the R value?
Here, sir, we are calculating R value for 0.507
Yes,
transmissibility.
yes, yes.
And that omega upon omega n, that is 1.24 is.
That actually that is the particular, but we cannot use that 1.24 omega by omega n ratio. So we need to do, how do we place our uh, isolators so that our isolation would be omega by omega n should be greater than 1 square root 2. We need to find out that.
Okay.
One thing is that you do not need to do the calculation. I have the availability of the isolator of that same time, same kind of like, which like, if I have the isolator which have the stiffness of 7 into 10 raised to power 6. Okay, so using that I'm getting omega n is equal to 127. How can I reduce this? Because my mass would be constant, mass is constant. How can I reduce my stiffness?
See,
What?
frequency means
How can I change
uh,
the frequency of that?
reducing by increasing stiffness. No,
No, that is
then
isolator is,
frequency will increase.
I I
Decreasing.
I have the isolators, same kind of isolators are available. So what can I do so that I my frequencies reduces? So that can be done like, I have the same isolator. If I put my two isolators in the series, did you get it? If I put two isolators in the series, how much then my stiffness would be the isolator stiffness? So my K equivalent would be the KB by 2. So it will reduce to how much? 3.5 into 10 raised to power 6 Newton per meter. So now my omega n would be K equivalent by M. So K equivalent is 3.5 into 10 raised to power 6 by 430 kg. So how much omega n I am getting?
90.22.
So that is coming out to be 90.21 radian per second. And now calculate the omega by omega n. So omega was the 157 and omega n is the 90.21.
Now it is 1.74. It is greater than root 2.
So it is coming out to be 1.74, which is greater than root 2. So that initially it is not satisfying with that. So either what we were doing, we are calculating R. If you do solve this, you will get R is equal to 1.75 from this. Okay. So from this you will get the omega and something you required 89 something, 89.7 or some 90 radian per second. So for this we can do what we can do. We can put two isolator in a series. Are you getting?
Yes, I'm getting.
If I have
Yes,
the,
sir.
if I have the available mass is like, let us suppose, like in the in the first case what we have considered, we have the available isolators only the same kind of stiffness properties. What if I have the only, this is the case one. What if I have only one isolator? What if, anyone? Anyone can tell me? Anyone? Am I audible?
Can we increase mass?
Yes, we have to increase the mass. If that we have the only available isolator. So to find out that it should be greater than square root 2 or over omega n should be like nearly 90 radian per second. So we can get it like kb divided by m is a 430 is already available. So we need some extra mass m dash. So you can calculate using this. You will get m dash nearly around 440 kilogram you need. So that extra mass you can attach to the machine so that you will get the effective isolation. So for this is a like not a like these are the simple questions, but for the isolation, what we have discussed in the question 4, that was the how do we solve the isolator if you have given a building. So now I hope you can solve the building with the if we have applied the isolator. Any doubt in this case? Any of the question? So in the next class, what do you want to study or you want some discussion kind of thing? What should we do in the next class? Anyone?
Hello.
Yes.
Okay. In the next class, uh, can do you get any previous year question papers? Like what type of questions? How many questions?
No, if those are not there, if those were be there, then we can discuss it because those are not with me. So previous year question papers I don't know. But if you do the solve whatever kind of problems we have solved during this live session or the assignments, those will be sufficient to solve those kind of problems, whatever you got in the exam. So in the multi-degree of freedom system, you won't get that much of the complicated problems. Simple two-story or the three-story problems, so that you can solve it easily. You should know the procedure, so that you can solve. You do not need to think about it. And for the generating, like the developing the equation, governing differential equation on those, you need some practice, some kind of questions, typical questions.
Because we will have a this numerical like we don't have any choice, right? Some of problems we like fill in the blanks also.
Yes, there will be some of the questions would be with the fill in the blanks. Some of the question would be the some like the choices, multiple choices, objective type.
Actually, I have a question in a week 10. Uh, can we discuss here or we can discuss in the next class?
You have the question related to assignment or what?
Yes, yes, assignment related to not. Uh, we have solved the question. Can I here?
Yes, you can ask if I will be. Let me find out what question you are.
Sir, I have also few doubts. Means not from assignment, but related to dynamics.
Yes, you can ask here. We have the 10 more minutes.
Yes, in assignment 10, sixth question.
Let me check.
Assignment 10 and sixth question.
Sir, can I ask my doubt?
Yes, you can ask. Let me first check what was the assignment question so that Yes, in the assignment 10, what was the now? Which question?
In sixth question, while calculating the uh, while calculating the peak response, right? And sixth question, 1 minute.
Sixth question,
I,
that beam question.
no, assignment 10.
Yes, in the.
Assignment 10. Sixth question means this is two-story,
Okay,
two-story
okay, okay.
frame.
Yes, yes, yes. I got it.
Okay, we have to find the peak displacement of first story
Yes,
due to explosion.
yes,
Okay, you have given the solutions,
yes.
but in our class, we have a they have solved using this I by m, like if you get
I by m omega.
yes.
Yes,
He- Here in our class, or if you see the uh, 1 minute that problem solving session 5, in,
okay.
in problem solving session 5, if you just see once in the fourth question, just I want to show. I don't want to waste your time. Just I want to just go to the fourth question. Fourth question of problem solving session 5.
Let me check. Yes, five. Yes.
Fourth question, use D'Humble integral, right?
In the
That
fifth
question,
one,
right?
you were asking for the fifth one.
No. In problem solving session 5,
Yes, in the five. Yes.
fourth question, fourth question.
In the problem
That
question five, in the fourth question. Okay, okay.
that blast loading, triangular blast loading.
That triangular blast loading is also the fifth one. The fourth one is the water
Yes,
tank
yes.
one.
Right. There, if you see that T less than TD, T greater than TD, right? We have
Yes,
a two responses, right? A free
yes,
vibration case and force vibration
yes,
case.
yes,
So, what I have done is in our assignment 10th question,
yes.
in assignment 10, sixth question, what I have found is I have found the omega 1 and omega 2.
Okay.
Okay, then I have found the T1 and T2.
Yes. T1 and so what was your TD by TN ratio?
Yes, 1 minute. That that was 1 minute. 0.089. T1 is 0.089. Okay, T2 is 0.178.
Like in the omega one was the 22 and the omega two was the 44.
22.36. Omega 2 is 44.721.
Yes.
Yeah, we got this T1 is 0.089 and T2 is 0.178.
0.281 and the 0.114. Okay. Yes,
Okay, 0.1.
your TD by TN and that is you are calculating. Okay.
Okay. Then here in both cases we have free vibration case, right?
In that both the cases your pulse shape doesn't affect, so that you will get the I by m omega n directly. Force vibration you can directly get to the ut is equal to I by m omega n sine omega t.
If T less than TD in D'Humble integral, we have derived uh, response. You can just see in the uh, problem solving session. We have found the RD value, RD is the equation. Can you see once? if t less than td,
Yes,
uh,
in the problem section 5, we have calculated TD by TL less than zero point 0.5, and we solve this also the I by M omega and sin omega t. Same.
actually my doubt is okay, why should we multiply this rd into uh, p not by static displacement, rd into static displacement? Can I
Yes.
multiply?
So in
Okay.
that question, whatever the question in the week 10 assignment, your TD by TN
Yes.
is less than 0.25 in both the modes. So your UT
Yes.
would be the I by M omega and sin omega t, and your I would be the 1 by 2 F naught TD. Okay. So
Okay.
actually, what happened that they have put the R1 as a I by M omega and as a representative type. So that is not like that. Like that is the I by M omega and directly. Nothing like that. You have to R is something RD. It is not like that. It is like they represent. They have to reduce the complexity in the calculation. Like they do not need to write it again. That I by M omega n. You can directly they have put it R1 is equal to I by M omega n like that.
Yeah, you can take, but I didn't take like that.
If you
I
take
found the
that I by M omega and you can calculate directly, you should get the answer. And
I'm not.
or for the I by M, what M you are taking, Mn or M symbol M, what you are taking.
No, M1 and M2. I have taken M1 and M2.
If you take an M1 and M2, you should get the answer. You should compare where you are getting the wrong, because the solution is correct, I think.
Okay, okay. I have taken. No, sorry.
And there
Yeah,
you
I have taken M1 and M2.
yes,
Yes,
generalize
that,
generalize M1 and generalize M2.
yes, yes.
So did you take that now? Did you take generalize mass or not?
Just I am seeing. I am seeing.
And then at the end, what they have done, they have combined the response of the first story, and to find the maximum response, they have done the derivation with that, and they are getting the t value with that, and on that t value, they are getting the values.
Okay, no. I take directly M1. I didn't take M1 M2.
Yes, you should take the capital M1 and capital M2, not the direct story M or story M.
Oh, okay, okay. Then okay, we will get answer, right?
Yes, you should do the capital M1 phi 1 transpose time the mass matrix time the phi 1,
Yes.
like
Understood,
that. You
understood.
need to do that. Those sort of type mistakes you are doing in each assignment and each and every assignment.
Yes, yes,
So you have to be careful.
yes. Thank you very much. I am getting
So
because from 2 weeks onwards, I am getting doubt on this, but I don't have time to discuss this. Okay, I am getting. Thank you very much.
you can ask those things on the discussion form. Like if I am not, then the someone from the whoever the TA of this course, they will answer definitely for that.
Yes. Okay.
Yes, some other student has also doubt.
Yes, sir. Sir, that IS code is there, that 1893/2016.
Yes,
In that equivalent static method, we calculate the base shear. Okay.
yes.
So that means for that structure in that particular earthquake region, that much amount of
Base
base
year would be
shear
generated.
will get
Yes,
generated. So we have to resist it by
yes,
designing it.
yes,
Okay.
yes.
So, but how it is distributed among the supports means that single value is for all the supports, or that base shear is getting divided into the different means for base, means there are many supports are there, column and foundation. So
So
is
we
it
are
getting distributed or?
getting base year for each floor. We can get it. Are you okay with that?
Yes, sir.
Each floor we can get it. So according to that, we can like in the actually in the design in the calculation analysis, what we do if the stiffness in the if or like we have the four columns, so we are getting our like the base shear for the all the four columns combined. So that will be divided in
Yes, we are
all the four.
equivalent.
Yes, that will be divided in all four,
Okay, okay.
like that. And for the base foundation, we will talk whatever the you have to design the foundation, whatever the your base year is coming, total base year at the. So that
Okay,
foundation,
that is coming to all the foundation.
yes, that is in the all the foundation. If your four column you have the four foundations, then it also divided into
Yes.
the four, the base year also.
Okay, 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 okay.
So that's how those
Okay, sir.
things work.
Okay.
And there was one more
Okay.
doubt you were asking, like you are giving, you have the some setup, and you are giving the.
Yes, sir. Yes, sir. Yes, sir.
So for that, actually, you can apply, you can attach your sensor or like accelerometer at any of the floor. Okay. So
Yes, sir.
if you want to find out your like the model frequencies, like let us suppose your mod is, yeah, your model is three-story, so you will be having three model frequencies. So you can
Yes, sir.
you can put at any floor, you will get the resonance in each three conditions, in each three mode. So you will get easily your model frequencies. But if you want to interested, if you are interested in the floor acceleration, floor displacement, then you have to put the sensor at each floor.
We have accelerometers,
Yes,
means three floor structure is there. In result, we have to find the by our analytical method modes.
yes,
Okay,
yes.
sir. For that, can we consider only stiffness and mass matrix? Is it okay, or we have to consider the that damping matrix also?
No, damping also you need to consider. Like if your damping, like it was model for the what, steel or something else, because in the reality there will be
Actually,
damping.
it is a aluminium column and aluminium slab model is there.
Okay, so you can find out the damping first, rather than doing that calculation first. Like you give some like some pull it pull it that model and leave it and
Okay,
record the vibration of that. And using that you can find out the like that logarithmic decrement. Using that you can find out the your uh, damping
damping
for that.
means that okay, that will be considered.
Yes, or either you know the for the aluminum, you what is the damping. If you know, then the you can find out the model
Okay,
damping,
okay,
and then you can solve it. Damping you need to take into picture, otherwise you will not get the, because in the reality there is always damping, nothing is ideal.
okay, okay, okay. And means we have to do the force analysis of multi-degree of freedom system,
Yes, you can do to find out the
and
model
that
frequencies.
okay, right hand side will be means whatever ground motion I mean giving means 100 hertz, 200 hertz
Yes,
that we have
because
to consider.
yes, you can give the range of frequency from 0 to 50 hertz, 0 to 30 hertz, or like that. You can give
Okay,
the frequency, and corresponding to that, you will get a Fourier curve or something, whatever the data acquisition system would you have. So from that, you will be get
okay.
easily over frequencies, model frequencies.
Mm-hmm. Actually, lab manual is not there, so I feel difficulty in all
No, there
those.
are a lot of videos available on the YouTube also. I think. I'll go through that.
Means about the means conceptual calculation is I didn't get anywhere.
Okay.
Also, they have asked the experimental mode shapes. Mean that is what means what.
Experimental mode shape mean like that you can get the like the uh, displacement history of the each mode, you each story you can get at particular,
Yes, sir.
like you have you know the mode, like the if you have the frequency at the mode 1, mode 2, mode 3. Okay, like let us suppose you have
Okay.
the like the now what you can do, you can apply that frequency to that mode. Like let us suppose you want to vibrate your your structure in the first mode. Okay, so that what you can
Okay.
do, you apply the frequency at that particular model frequency for the particular mode, and then you measure the displacement at the each floor. Okay, and after getting that
Okay.
you can make a plot, how your like plot is look like in the structure. You can like in the graph you can show like that your three-story graph, and then you can find out that data how your it is coming out to be that. That is the thing, I think.
Okay. Okay. There are so many experiments. Means 5, 6 experiments are there.
So you are the
And
teacher at that college, assistant.
yes, sir. Yes, yes, sir. Yes, sir. I am assistant professor, and means I have not studied this dynamic lab anywhere, but in that college there is a dynamic lab is established,
Which college you are
and they
in?
have. I am from Rajaram Bapu Institute of Technology, RIT. It is in Sakrali, Islampur, Sangli district.
Okay.
So there are so many like dynamic vibration absorber is there. Then dynamics of one span, two span beam.
Yes.
Six experiments are there. So it gets difficult. Lab.
Once you will
Theory
do
gets
that,
easy because of the.
once you will get like do that once or twice, then you will be get habitual for those things.
Yes, 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 yes.
So anyone has
Means
any
this
doubt?
course helped me a lot while teaching. Means conceptually getting clear. So in front of student, I am lot more confident.
Okay, okay, good.
Only that lab issue is there.
Okay, okay,
I will sort out.
okay.
Sir, one
Hello,
more
sir.
question, last question, sir.
Yes,
As we discussed that resonant condition is okay for single degree of freedom system with
your
frequency matches,
your voice. Yes, for the single degree freedom, your frequencies matches. Yes, then
and that for multi-degree of freedom system we have different frequencies. So is there resonant means occur resonant condition in that case also?
yes, that will be happen.
Means for which frequency? Suppose 3 degree of freedom and we are
Yeah,
having three
like yes,
frequencies.
three. You have the 3 degree of freedom. Then the apply like one you can do the frequency from 0 to 50. Okay, of that system,
Okay,
and you get the response and you plot that. So those three frequency at those three frequency you will get the peak
okay,
like that.
okay. So
Sir,
means
uh, when we will have another class, you were telling we have
Yes,
another
that would be
session.
the extra session. I have like filled that Google form on the for the Thursday from 6 to 7 for only for the 1 hour. So wait for the NPTL team. They will email you regarding those things.
Now, can we change that date?
No, that I have filled earlier, so now it cannot be changed. So because I also occupied with this course from last 3 months, so now I want also want to get rid from this because of that I am very occupied with this course. So
Okay, in that class, we will discuss about all the.
yes, in the last class, I will come up with the 2 3 problems, and in general, if you have any doubt related to all the 12 sessions, we can discuss those things.
sir,
Okay.
when will be that session?
That is on the Thursday. That's the same time,
Okay,
6 to 7 this week, upcoming day after tomorrow. So
okay, okay, sir. Okay,
so that will be informed by the NPTEL team.
That
okay,
will
sir.
also
Okay,
include in our Google Drive, sir.
Yes, those material and that video will be uploaded at the same place.
Okay, okay. Thank you, sir.
Okay. If you
It's
have any,
nice.
okay. Thank you, sir. Thank you so much for support.
Thank you,
okay.
sir.
If you don't have
Thank
any
you.
doubt,
Thank you so much, sir.
okay, everyone, thank you for joining.
Okay,
Thank you, sir.
Okay, okay. If you don't have any doubt, you can leave the session.
okay, sir. Okay.